Ever try to time something, but right in the middle you get interrupted and you have to start all over from zero? It's incredibly frustrating. In industrial automation, machines deal with this exact scenario using what's called a non-retentive timer, or a TON. Think of it like a spring-loaded stopwatch. As long as you hold the button down, it counts. But the moment your finger slips, the hand snaps right back to zero, losing all its progress. If a conveyor belt needs to make sure a path is clear for exactly 3 continuous seconds before starting up, a TON is perfect. If a sensor detects a stray object at 2 seconds, the timer drops, forgets that progress, and demands a full 3 clear seconds once the object is gone. But sometimes you want a machine to remember. That's where the retentive timer, or RTO, comes in. This acts like a digital stopwatch with a pause button. If you cut power to the machine, the timer freezes its exact progress and waits. When power comes back, it resumes right where it left off. This is exactly what you need if you want to track the total running hours of a massive factory motor. It accumulates time over hundreds of shifts to tell you exactly when it's time for maintenance. Controlling time on a factory floor comes down to this single choice. Does the machine need to forget its progress or remember it? Inside the programmable logic controller, or PLC, both of these timing methods share the same digital structure. This diagram shows us what that structure looks like: a single block containing 2 number boxes and 3 indicator lights. The 2 numbers are your time values. The preset box, or PRE, is your target time. The accumulator box, or ACC, is the live running total that counts up to meet that target. Now for the 3 lights, which programmers call bits. The first is the enable bit, or EN. This is the finger holding the stopwatch button. As long as power flows into the timer block, the enable light stays on. The second light is the timer timing bit, or TT. This tells you the internal gears are actually turning. It stays lit only while the accumulator is actively chasing the preset. Finally, there is the done bit, or DN. This is your alarm bell. The exact moment the accumulator matches your preset, the timing stops and the done light turns on. These 3 simple lights, enable, timer timing, and done bit, form a universal language. They allow the PLC to communicate the exact status of a countdown to every other piece of equipment on the factory floor. So what happens to those numbers and lights when the input signal is interrupted? For our spring-loaded, non-retentive timer, it suffers instant amnesia. The moment the enable light turns off, the other lights go dark, and the accumulator wipes completely back to zero. Our digital stopwatch, the retentive timer, handles this differently. When its enable light turns off, the accumulator stubbornly holds on to its exact value, waiting patiently for power to return. But this creates an interesting operational trap. Because the retentive timer never forgets, once the accumulator hits the target and that done light turns on, it stays done forever. It becomes useless for the next cycle. To fix this, programmers must use a specific tool called a reset instruction, or RES. You have to write a separate line of code that acts like a reset hammer, explicitly forcing the retentive timer's accumulator back to zero, so it can start over. Retentive timers give a system the ability to track maintenance cycles over several months, but they demand that the programmer takes manual, deliberate responsibility for clearing that memory when the job is done. There is a hidden reality to all of this. A PLC timer does not actually sit there counting individual milliseconds in the background like a wristwatch. This diagram illustrates what really happens. The PLC operates on a scan cycle. The processor acts like a high-speed scanner, sweeping through thousands of lines of code over and over. It only checks the timer's math when the scanner beam passes directly over that specific line of code. When the beam hits the timer, it simply looks at the master system clock, compares it to the last scan, and calculates the difference. At 4,995 milliseconds, it sees the target hasn't been met yet, so the done light stays off. But the processor has to finish scanning the rest of the machine before it can loop back. If the 5,000 millisecond target arrives while it's busy elsewhere, the timer misses it. By the time the scanner beam returns, the clock reads 5,015 milliseconds. The timer successfully turns on its done light, but the accumulator records that overshoot value. That 5,015 milliseconds is the true exact amount of time that elapsed before the machine's logic could actually react. Timer accuracy in industrial automation isn't about having a perfect internal clock. It depends entirely on how quickly and frequently the computer's scan cycle can look at that clock. So how do you choose the right tool? If you need a fresh, clean delay every single time an action happens, use the spring-loaded, non-retentive timer. If you have a system that needs to keep running for a specific amount of time after it's been turned off, like keeping a cooling fan running for 5 minutes after a hydraulic pump shuts down, you use an off-delay timer. And if you need to track cumulative time across dozens of shifts and power cycles, you use a retentive timer. Just remember to write your reset instruction. Mastering time in an industrial facility requires choosing the exact memory behavior needed to keep massive machinery safe and predictable.